Hey everyone, and welcome to the Mastering Docker in 40 Minutes course. The goal of the course is not just to memorize Docker commands, but to understand the mental models behind images, containers, volumes, networks, services, and other concepts. If you're new to Docker, watch it from the beginning, and if you already know the basics, use the chapters to jump the part you need. Hope you enjoy and don't be judgy. Before Docker, deploying an app meant one thing: hope. Hope the server had the right OS, hope the right versions were installed, and hope nothing broke. There is a reason Docker shows up in almost every backend job description today. Because works on my machine is not a deploy strategy. Docker exists to fix this. In this video, I will show you what Docker actually is, why developers use it, and the only commands you really need. Modern apps depends on a lot of things: language versions, system libraries, environment variables, external services. When those don't match, things break. Docker gives us one simple idea: control the environment, and you control the behavior. Here is the simplest way to think about Docker. Normally, your app runs directly on your machine. This is just a tiny Python app with a fast API web server. Right now, this app is running directly on my machine, and that's the problem. If I send this code to someone else, there is no guarantee it behaves the same. Other guy may have another version of Python or a fast API. Docker adds a thin isolation layer. Your app still runs as a process, but now it runs inside a container. That container has its own file system, own dependencies, and own environment variables. But it still uses the host OS kernel. That's why containers are fast. So when you're shipping the container, you're not just shipping the code, you're shipping the exact environment your app expects. If it runs in a Docker container, it will run the same on your laptop, server, or cloud. By the way, Docker is not a virtual machine. Virtual machines simulate hardware and run a full guest OS. Containers don't do that. They share a kernel, which makes them lightweight and fast, and you can run dozens of containers where you would struggle to run a few VMs. To keep things simple, let's quickly cover the core concepts. An image is a blueprint, basically a recipe. A container is a running image. A Dockerfile is just instructions for building an image. Docker Hub is a GitHub but for Docker images. Don't worry about memorizing this, let's run something. First, let's make sure Docker is installed. If you see a version number, you're good to go. Otherwise, just visit docker.com and download Docker desktop application. Now let's run a real service. This command might look a bit long, so let me break it down real quick. Docker run starts a container. Flag D runs it in the background. Flag name my Nginx, give it a readable name. Flag P maps port 8080 on my laptop to port 80 inside the container. And Nginx Alpine is the image, a lightweight Nginx server. What just happened? Docker didn't find the image locally, downloaded it from Docker Hub, created a container, and started it. Let's confirm that it's actually running. Docker PS shows all running containers. Here you can see the image, the status, the ports, and the name. Now let's see if it works. I open localhost 8080 and there it is. Nginx is running. I didn't install Nginx on my machine, I just run a container. Now let's take a look inside the container. This command runs a shell inside a running container. And now watch this. This is not my machine. This is a container. It has its own file system, own processes, and own environment. Let's exit the container. Every container produces logs. Docker logs shows that output. This is incredibly useful for debugging. Now let's stop the container. Docker sends a seek term signal. The container shuts down gracefully. After that, we can remove it. In the previous video, we ran ready-made Docker containers. That's cool, but it's not how Docker is used in real life. In real projects, you build your own images. We will do exactly that. We will write Dockerfile, build our own image, and run a real Python application. Let's clarify one important thing. A Docker image is not a running app. It is an instruction, a template, and the container is what you get when you run that instruction. So image is a recipe, container is a cooked dish. Everything starts with a Dockerfile. Dockerfile tells Docker how to build the image. Dockerfile builds this image, and then we run containers from it. Docker images are built in layers. Each instruction in a Dockerfile creates a new layer. Base image, dependencies, source code, startup command. Docker cache these layers. That's why Docker builds are fast and reproducible. Let's look at the project. This is minimal Python app, nothing fancy, just enough to show real Docker usage. And now let's try to make a Dockerfile for this project. We start from the command from, which defines a base image, Python 3.12 slim, small, fast, and good enough for most production apps. This sets a working directory inside the container. From now on, all commands run from here. Then we copy only the dependencies file first. This is important for caching because this command makes its own layer. Here we install Python dependencies. This layer will be reused as long as requirements don't change. Now we copy the rest of the application code. This layer changes most often. That's why we put it in the end. Expose the commands which port the app uses. It doesn't publish the port, it's just a small hint for another developer. And finally, this is a command that starts the app. At this point, the image is fully defined. We're not running anything yet, we just described how the image should look. So now let's turn this description into real image. Docker reads the Dockerfile from top to bottom and creates layers one by one. After the build finishes, the image is ready to use. Let's run the container. We map the port, start the app. After that, we can check our app. We can use curl and see what happened. And it works. Same result, any machine, same Docker image. Also, I would love to show you some common mistakes. They are using huge base images without a reason, copying all files too early, putting secrets into Dockerfile, and forgetting about Docker ignore at all. Small details make big difference. Today you learned what Docker image really is, how to write a Dockerfile, how layers work, and how to build your own image. You built a Docker image. That's nice, but right now it only exists on your laptop. How do you run it on the server? How do you share it with your team? How do you deploy it without copying files around? Today we are talking about Docker Hub, where images actually live. To understand Docker Hub, we need to understand what Docker registry is. A Docker registry is just a place where Docker images are stored. Think of it like this. GitHub is for source code. Docker registries are for Docker images. The most popular registry is Docker Hub, and by default, Docker pulls images from it. In this video, we'll do 4 things. Take an image, tag it properly, push it to Docker Hub, and run this image in a different machine. The first step is login. Docker needs to know which account is allowed to push images. If you don't have an account, now is the best time to create one. Go to hub.docker.com and sign up. The next question is, how does Docker decide where to push images? That comes down to image names. A Docker image name always has three parts: username, repository, and tag. Username is your Docker Hub account, repository is the image name, and tag is the version or label. Now let's see how it works in practice. Here is a tiny project which is small Flask web server. Let's make an image from it. Here is our Docker demo image. Now we can run a container. Let's see how it works locally. It works fine. Now we can prepare our image to Docker Hub. Docker tag commands put together the image for pushing to Docker Hub. Then we can push it using Docker push command. This is the moment the image goes to the cloud. Docker splits the image into layers. It uploads only what's missing and reuses everything else. That's why the first push is slow and the next one are fast. Let's open Docker Hub. Here is our repository. You can see the image name, the tags, the last update time, supported OS. This is now a real image in cloud. Anyone can pull it and run it. Let's SSH to the new clean machine. Here I will only install Docker and no other dependencies. We're gonna use some simple commands. So now the server has nothing installed except Docker. No Python, no Flask, no setup. I just need to pull the image. Now we check that image is here. The image is ready, so now we can run our container. Let's make sure that it works just fine. And now we have the same result as we had locally. Let's just quickly recap what just happened. I built a Docker image on my local machine. I pushed that image to Docker Hub. Then I went to a completely clean server. No Python, no Flask, no virtual environments. I installed Docker, pulled the image, and ran it. That's it. Same image, same behavior, different machine. This is the core idea of Docker. Build once, run anywhere. Before we finish, I want to show you 3 simple best practices. Rule number 1. Always use explicit tags. Never rely on latest in production. Latest is not predictable. Production needs certainty. Rule number 2. Never push secrets into images. Not API keys, not passwords. Environment variables are not secure storage. Rule number 3. Know what a registry doesn't do. A registry stores images. That's it. It doesn't give you load balancing. It doesn't give you SSL termination. It doesn't run containers. Docker Hub is not a god. It's just a storage. In the next video, we will talk about the biggest Docker pain point: data. Containers die, data shouldn't. Hope you enjoy. See you next time. Docker is great at running applications, but there is one thing it reads very aggressively by default. That thing is data. And to understand why it happens, we need to start with how containers actually work. A container is basically a process plus a temporary file system. That file system belongs to the container. So as long as the container is running, files exist. But once the container is removed, that file system goes with it. And this behavior leads to a very common surprise. Let me show you what I mean. I start a container, I create file, everything looks fine. Now I remove the container, I start a new one and try to read that file again. And it's gone. At this point, Docker is doing exactly what it promised. So the next question is obvious. If file disappear with the container, where should important data live? Because in real applications, we don't store just text files. We store databases, logs, user uploads. And this is where volumes comes in. A volume is a storage that lives outside of the container. The container doesn't own it, it just mounts it. So when the container goes away, the data doesn't. Once you see it that way, volumes stop being mysterious. Let's make this concrete. First, I create a volume. Then I start a container and mount that volume inside. Now, anything I write into that directory is no longer tied to the container itself. It's tied to a volume. So when I remove the container and start a new one, the data is still here. We got a new container, but we have the same volume, which has the same data. Now you might wonder where this data actually lives. And the key idea here is this. Docker manages volumes for you. You don't need to know the exact path, you don't need to touch it manually. This abstraction is intentional, and it's what makes volumes safe. Once you understand what a volume is, the next logical question is, are there different ways to connect data to containers? And yes, there are two. The first one is named volumes. This is a Docker managed storage. Docker decides where the data lives and how it's handled. Because of that, named volumes are the safest option. The second option is bind mount. Here you mount a specific folder from your host machine directly into the container. This gives you more control, which is great during development. Change a file on your machine, the container sees it immediately, but the same power also makes bind mounts risky in production. So far we talked about the simple files, but the exact same rules apply to real services, for example, database. First we create a volume. Now we start Postgres using volume flag v. Let's create some data, a table, one row. This data is not inside the container, it's inside the volume. Now we insert one record and check it. Now we remove the container. As we know, the containers are cheap and disposable. We recreate the container using same image and same volume. And the data is still here. The container changed, the data didn't. So here is a quick summary I want you to remember. Containers are disposable. Important data should live in volumes. In production, use named volumes. In development, bind mounts are usually fine. Now that we know how to keep data alive, in the next video we will connect containers together using Docker networks. Hope you enjoy. See you soon. My backend works, my frontend works, but the moment I connect them, everything breaks. In this video I will show you why containers can see each other and how Docker network fixes that. I have a small Flask backend image. It runs a web server and listens on port 5000. And I have a frontend container which is just Nginx. I'm running them the most basic way possible, no custom networks, no flags, just two containers. This looks fine until the frontend tries to call the backend. Let me get into the frontend container and try to curl the backend application. We got some bad response, and this is where most Docker network confusion starts. Here is a trap. Inside a container, localhost doesn't mean your computer. It means this container. So when the frontend calls localhost, it's just talking to itself. So our curl fails not because Docker is broken, but because these containers don't know about each other. They are isolated by default, and this is intentional. So the question is not why doesn't this work? The real question is how are containers supposed to talk to each other? This is what Docker networks are for. A Docker network is a private virtual network where containers can actually see each other. When containers share a network, they can communicate, they get automatic DNS, and they can reach each other by name. Think of it like Wi-Fi for containers. So now let's practice. Let's make our first network by using network create command. Also, we can use network ls to see what other networks we got. After that, we can use inspect command, which show us all information about this network. Right now, this network is empty, no containers are connected, so let's fix it. We will again run our containers, but now we will use network flag. Both containers are now inside the same Docker network. I'm not exposing any ports yet, this is internal container-to-container traffic. Let's again get into frontend container and try to curl backend. And it works just fine. I didn't configure DNS, I don't know the IP address, I'm just using the container name. Inside every Docker network, Docker runs a small built-in DNS server. When a container joins the network, Docker automatically registers its name and IP. So, inside the Docker network, container name equals DNS name. So now let's take everything we learned and put it together. A real backend, a real frontend, and Docker network between them. We have exactly the same Flask backend image. This is very simple frontend. When the page loads, it sends a request to API hello and prints the response to the page. Notice there is no host, there is no local host, no IP address, just a relative URL. We got nginx.conf that serves the static frontend, but here is the key part. Requests to API are forwarded to backend 5000, and I will repeat again, backend is not a host name from the internet, it's a container name. And also we got Dockerfile for frontend. This image is very simple. We take nginx, copy the HTML file, and replace the default config. Let's build our frontend image. Note that flag F points to a custom Docker file, and flag T gives the image a readable name. Also, it's good to mention that dot in the end gives us the context where we can find our Docker file. Also, let's check that all images are ready. And again, we are creating our Docker network by using Docker network command. And now we can run our container. We start with the backend. Don't forget about network flag. After that, we can run frontend container. Besides network flag, we need to forward port to make application accessible from our machine. Now we can check the result. In the browser, we open localhost 8080 and it works. To sum up our experiment, the browser talks to the frontend talks to the backend, all through the Docker network. No IPs, no magic, just Docker networking. In the next video, we will take the exact setup, same backend, same frontend, same network, and replace all of this with a single Docker compose file. Hope you enjoy. See you soon. By now, we already know how to use Docker. We can run containers, we can connect networks, we can attach volumes, but the problem is there are a lot of commands and even more flags. Docker run, network, volume, env. and that's just the beginning. Now imagine this, all of that in one file and only one command. This is exactly what Docker Compose is about. On the left, classic Docker, multiple Docker run commands, hard to read, hard to remember. On the right, Docker Compose. One command we need, Docker Compose app. This is the reason Compose exists. So what Docker Compose is? Docker Compose is a tool. It allows you to describe multiple containers and how they work together. You describe which containers you need, how they are connected, which ports and volumes they use, and all of this lives inside a single file, Docker Compose YAML. Docker Compose is used everywhere. Local development, pet projects, demos, CI/CD environments. Compose is a daily tool for a huge number of developers. However, it's important to clarify that Compose is not Kubernetes. It's not a production orchestrator for huge clusters. But for pet projects, demos, local development, it's absolutely amazing tool. In this video, we will build a very simple stack reusing code from previous video. A browser talks to a front end, the front end talks to a backend, multiple containers, one compose file, one command to run everything. Simple but very realistic. Let's start from scratch and write our first Docker Compose file. Even if you never used Compose before, the file should be readable. The most important section in Docker Compose is services. Each service is just a container, nothing more. And the service name is very important. It becomes the DNS inside the Docker network. Inside the service, we describe the image or build context, ports, environment variables, and dependencies. So service is not an abstraction, it's just a regular Docker container described in a nicer way. We made a backend, now let's switch to the frontend. We are using not default Dockerfile name, so here we should specify that. Also, we know that frontend is our entry point to the application, so we need to specify two ports. The external port 8080 of our machine and the port 80 of frontend container. Also, we add depends on, which controls startup order. Ports are often confusing, so let's clarify this. We use ports only when we want to access a container from the host machine. Between containers, ports do not need to be published. And now the fun part. When Docker Compose is ready, we can use Docker Compose app command. Compose builds the images, creates a network, and starts all containers. We just launched multiple containers with a single command. To understand the funny part, let's compare two different flows. Thanks to the Compose, we need only one command. Now let's make sure that everything works. Everything works fine. Docker Compose treats the whole stack as a single unit. We can start it, stop it, and view logs from all services at once. Now let's make a little upgrade and use more capabilities of Docker Compose by adding database. Firstly, we need to change a little our Flask app. Now in the app, we connect to the Postgres and return the first message from messages table. And also we add our new dependency to requirements file. Now we can change our Docker Compose file. First, we need to pass environment variables, which we use in Flask application. Now we can define our new service. We will call it DB. We don't need to have any Docker files, so we can use image from Docker registry. So here we define what image we will pull. We also need some environment variables here, so let's define it. As long as we want to have persistent database, we need to define volume. Here we describe where DB files will live. Also, don't forget about the volume in the end of the file. Now let's start our application again. As you remember, in our Flask application, we go to Postgres, we check table messages and get the first message. Now we need to actually create the table and insert some message. The fastest way to do it is to use PSQL. Here we are logging to database with user demo, with password demo, and with two simple commands we are creating the table and insert the message. Let's check that everything works. And we got hello from Postgres now. In the next video, we will talk about image optimization and best practices of Docker. Hope you enjoy. See you soon. Let's start with a very common architecture. We have a backend API, and it connects to a Postgres database on startup. Here is the problem. The Postgres container starts very fast, almost instantly. But the database itself becomes ready to accept connections only after a few seconds. Docker sees the container as started, so the backend container starts immediately. The backend tries to connect to the database, connection refused, the backend crashes, Docker restarts it, and we got an infinite restart loop. So the question is, why does that happen? It happened because in our compose file we used only depends on keywords. As we remember, depends on give us only startup order. So when we write in Docker Compose depends on DB, it means that at first we need to start DB container, then we can start our application. Docker started the database container, but Postgres itself is not ready yet. This is a key idea. A container being started doesn't mean the service inside is ready. To save us from crash, we can use healthcheck. The database now has a health check, and the backend waits for the database to become healthy, not just started. As you can see, here we use a special command that shows us if DB is ready. Also, we can set timeout of this command, different retries, and interval for this command using. Now the backend will wait for the database readiness, not just the container startup, but for the service is actually to be ready. So now let's make sure that it works. And it works just fine. Firstly, we set up database, we check that it works, and now our application can start without any errors. Now let's talk about image optimization. If your image weighs gigabytes, that is not normal. If it builds slowly, that is not normal either. Image optimization is not about aesthetics, it's about speed, money, and stability. Here are some tricks that really can help us. So the first tool is Docker Ignore. By default, Docker sends the entire project directory into the build context. That includes Git history, virtual environment, node modules, logs, datasets, everything we actually don't need. Docker doesn't know what you need, so it just takes everything. Here is a small example of how it looks. The second thing I would love to remind you is Docker cache. As you remember, every command in Dockerfile is a specific layer. So the rule is simple. If this layer is rarely changed, we can use it higher. And if it changes a lot, we can use it lower in our Dockerfile. The next thing I would really love to focus on is multi-stage building. One of the most common Docker mistakes is building one image for everything. For building, for running, for production. And in the end, production contains everything we don't need. To understand the idea more clearly, let's use Golang example. In Go, we usually compile the program, and as a result, we have a binary file that we can execute. And now ask yourself, do we really need to copy all this code we have to image? Of course, no. We need to have only the binary file which we can run. So the solution is to make two stages. The first stage where we can build our program, and the second stage where we just run our final program without code, without dependencies. So now let's make a small test. Here we have a small application. We just print hello from Go. we have some requirements, we have some dependencies, and we have a average Docker file with only one stage. And also we have multi-stage Dockerfile. Here in the first stage, we're just making executable file. In the second stage, we are pulling the smallest image we can. We copy the executable file from the first stage and run it. Now let's see what these tricks give us. We are building two images using different Docker files. Now it's time to compare our two images. As we can see, the difference is huge. It's about 10x. Just imagine how helpful this trick could be in production, where you could have much more dependencies. This trick is also useful in other languages like Python. For example, here we also have a small application and we got huge requirements, like really huge. So it's definitely a good case to multi-stage Dockerfile. In the build stage, we install dependencies into root local. This directory is not part of the system Python. It's just built artifact. So we don't copy Python, we don't copy pip, we don't copy different compilers from dependencies. We copy only the result of the build. Here you can see the result. It's not as cool as in Go, but it's definitely worth it. The last thing I would love to mention is Docker cleanup. Even with perfect Docker files, the system will slowly rot. Stopped containers stay, old images, volume,